Hello everyone, my name is Xiaoxiong Zhang. In this presentation, I will introduce my work Spatial Graph Regularized Correlation Filter for Visual Object Tracking. This work is also collaborated with Dr. Sajid Javid, Dr. Lam Kama, Dr. George Diaz, and Dr. Noble Virgi. In my presentation, I will first start with the background introduction and then talk about the challenges in visual object tracking. Following that, I will review the discriminative correlation filters for visual object tracking and its research gap. Then I will talk about the proposed methodology and experiment results. Finally, I will wrap up the presentation with the conclusion and acknowledgement. In computer vision, visual object tracking is a task that, given the target state in the first frame, the main goal is to estimate the target locations between the consecutive frames, as shown in the figures. Visual object tracking include a single object tracking and multi-object tracking. In this research, we focus on the single object tracking. Visual object tracking is an essential task across many applications, including video surveillance, for example, like people counting, traffic surveillance, and visual reality. Also in other fields like robotic system, human action recognition, medical image processing, also using the visual object tracking. Visual object tracking is still a very challenging task when the target object suffers from appearance variation challenges. The figures here are some examples for showcasing the challenges, like illumination variations, the object rotations, object occlusions, the low resolution object, and the scale variations and background clutter. Over the past few years, many methods has been proposed to address these visual object tracking challenges. Among the most representative methods, the discriminative correlation filters method has been widely employed in visual object tracking for their efficiency and remarkable performance. In here, we call the discriminative correlation filters as DCF. In DCF methods, the correlation filter is first trained on the target object using its circular safety sample through minimizing the least square loss. And then the target is detected between the consecutive frames by convolving the chained filter via fast Fourier transform. The success of DCF mainly lies in the circular safety sampling operation of the target. However, the underlying assumption at this training and testing process produce unwanted boundary effects, which degrades the performance in the challenging scenario. Several attempts has been made to improve the visual object tracking performance using DCF, such as the method adding the spatial regularization, convolution neural network features, background aware DCFs, and spatial temporal regularizations. While these methods showcase a significant progress, but they still could not cope well with the target shifting challenges, and they have been criticized for the computation complexity. We incorporate the, in here, we propose to incorporate the structural constraint to solve the limitations. Incorporating structural constraint in the DCF framework is to maintain the spatial structural consistency of the target object. To the best of our knowledge, such constraint has not been proposed before in DCF framework. So our proposed algorithm consists of three main steps: the feature extractions and the construction of spatial graph and the DCF objective function minimization. I will introduce these three steps one by one. In the deep feature extraction step, we first crop the target object from the image, and then use the pre-trained VG19 network to extract the hierarchical deep features from the cropped image using 3 convolution layers. Later, these deep features are used for training the DCF, and we construct the spatial graph DCF based on the classical DCF formulations as shown in this equation. One shortcoming of this classical DCF is that it observes the undesired overwhelming boundary effect because of the periodic assumption that, and it results in the performance degradation. To tackle this issue, we propose to incorporate the structural constraint to maintain the spatial appearance structure of the target in the DCF, which is using the adjacent matrix between the circular shifted version of the target in the graph structure. Here, A is the adjacent matrix. It encodes the weight and the connectivity of the graph. We implement this constraint by enforcing the resulting correlation filter omega to act as an eigenvector of the spatial graph Laplacian matrix L and constructing our final objective function here. By introducing the spatial regularization into the DCF framework, we ensure that the resulting correlation filter maintains the spatial structural consistency of the target object. To solve the formation objective function, we use the iterative ADMM method, where we introduce two auxiliary variables g and h to convert the objective function to a Lagrangian formulation, and solving one variable while fixing the other one, using the following iterative equations. To evaluate a proposed trackers, we conduct a series of experiments on 4 public datasets, including TC128, VOT 2018, UAV123, and the OTB100 dataset. The figure reports the visual result comparing our tracker with the 6 state-of-the-art trackers on the 9 challenging sequences. Comparing to the proposed tracker, majority of the compared trackers do not perform well in all cases except for the BOLD 5 and the CAR7 sequences. In comparison to the SRDCF and the STRCF, our proposed tracker, SGDCF, handle this sequence well under the fast motion, motion blur, and occlusion scenarios. The deep features-based spatial graph facilitate the proposed tracker to handle these compressed scenes. As a result, the response map predicted by our proposed tracker is more accurate for the target localization, especially in diving, board, and fish. And overall the visual evaluation indicates that the proposed tracker performs excellent on these sequences. We also quantitatively evaluate the tracker comparing the state-of-art tracker on the 4 dataset. In OTB100 dataset, as the results shown in the figure, we can notice that the performance of our tracker exceeds its best competitor by 2.3 and 2.6% margin in the precision and success respectively. And in UAV123 dataset, the result reported in the figure indicate that the success of proposed tracker with a precision and success score of 0.0823 and 0.0768, preceding its competitor with a large margin. And in TC128 dataset, the proposed tracker also significantly outperformed all the comparative trackers. And on VOT 2018 dataset, we use a different matrix like accuracy, robustness, and the expected average overlap as shown in the table to evaluate the tracker. And the proposed tracker has achieved the best performance in all 3 measurements. To conclude, in this work, we propose a DCF-based tracking algorithm variant by enhancing the graph-based spatial structure consistency constraints. We are evident that the encoding the graph structure into the correlation filter results in a significant improvement over the baseline, as well as the other previous proposed constraint in the current state-of-art tracker. In future, we will consider include the detection model to improve the long-term tracking performance. This work has been supported by Halifax University of Science and Technology. Thank you for your attention.